done with the pre-show thing, did everyone pick up both pages of the sky charts at the back? Sheet 1, sheet 2?
Yep.
Okay. Saves me trouble passing things out later. Next month is just basically going to be an extension of the series. We started off with the solar system. We talked about constellations. We then did the eclipses. Last month we did stars. And this month we're going to do the deep sky objects. Next month we're going to do a little bit of hands-on things. We're going to talk about using a telescope and binoculars for observing, and also planning your time, because when you go out and stand behind a telescope, you don't have time to mess around and try to get organized at that time. You get tired too quickly. And it's, you know, when it's bedtime, you go, no more viewing. So, the show today, or the lecture today on deep sky objects, relates to either this and this.
Can I turn out the lights in the back? Is that acceptable? So you see that better?
Messing you up? Yeah.
It's fine. I got it.
Thank you.
We're going to wait for the last couple of people here. Okay, deep sky is a little bit of a takeoff on the near and the far. Near is things, near things are things that you can imagine. You can see them, they're close to us. Things like the moon and the planets, relatively close. Things that are further away, you need a telescope. You can't see these things with the naked eye, and a telescope and binoculars are the best way to do it. On the sky charts, on the second page there, as I told you before on past lectures, the important thing from my perspective is what you have to have a telescope to see, and what you have to have binoculars to see. The naked eye things, I know about them anyway. But the deep sky objects using the telescope are all, the ones that are listed on page 2 are all on the map on page 1. And we'll look at the sky chart in order to find some of the things that I'll show you slides of. Pardon the English there. My prepositions sometimes get misplaced at the end of sentences. Okay. Part 1, galaxies. Part 2, nebulas, clusters, double stars, and then the etc. Now, before we can talk about these things, we have to go back to not just the near and the far, we also have to go to the big and the little. So let's look and review big and little. Those of you who have been to these before recognize that we've got planets down here. We've got the sun up here. The sun is much larger than, say, the Earth. We all grasp that. Sometimes when you're looking at things outside or even looking at an eclipse, you don't recognize just exactly how big the sun is. This helps you a little bit there. And as big as the sun is, the sun over there is not nearly as big as some of the other stars that we'll be talking about. And part of this also becomes a matter of looking at the distances. The sun is 8 light minutes away. Arcturus is almost 37 light years away. So it's much further away than the sun, and that's why it appears as a star, even though it's much larger than the sun. We have a different set here. We now see that Arcturus, which was huge on the last slide, is now relatively small compared to Betelgeuse and Antares. We also see here Rigel, and the reason I mention Rigel is because we'll see it on the slide later on, and I want you to remember it. It's not as big as Betelgeuse, but actually it's much brighter as a star. And there's a hint here. That's red. That's not red. Rigel is a much younger star, and it's throwing out white light as opposed to the redder wavelengths, and it's brighter in the sky. So they're pretty far away, both of them, but Rigel is actually brighter than Betelgeuse in Orion. So now we have that, big and little, well in mind, and we can talk about some of the other things. And I'm not going to read it to you. Kind of embarrassing to tell you that I wrote it. It's not the way that your parents told you as a child. But we do have a few things up here that tell us about astronomy. We talk about spectrums, we talk about redshift, and we talk about the brightness and distance and other blinky stuff. But all of this goes to show that astronomy is not that difficult if you can put it into a little bit of a twinkle, twinkle, little star nursery rhyme. Now, to go back to that spectrum business that I was telling you all about before, the business of using a prism to separate the spectral lines on a wall went back to 1801, and we had Wollaston who recognized for the first time that there were dark lines in the spectrum. Most of the time when we look at the spectrum, we do not see dark lines. Look at the spectrum here real fast. This is what we normally think of with the spectrum. We have the visible light in a very narrow band here. And when we take it through a prism and shine it on the wall, we get this nice continuous red, orange, yellow, green, blue, indigo, violet spectrum, little rainbow on the wall. And this is what we're talking about with the visible spectrum. And this is what Wollaston looked at and found all these dark lines. Before we go back to Wollaston, I'll mention that we also have wavelengths that we can't see, the infrared and the ultraviolet. We know that we can't see X-rays, but X-rays can look through our body. Gamma rays are generated by stars and are dangerous. And without our atmosphere, we would probably die from those. Well, no, we would never have evolved. It's complicated. Okay. Low end of the spectrum, high end of the spectrum, and we think in terms of the high energy here and the low energy here, and I'll repeat that later. We'll get rid of this. Go back to Wollaston. 1817. Remember, this was 1801, and this is 1817. That concept of the dark lines was taken a little bit further. And Fraunhofer took a much closer look and spread them out more on the wall, and this is what he saw, this mess here. How can you make any sense out of that? Well, a little bit later, 1859, you had Kirchhoff and Bunsen. And this was kind of neat because I was informed in making these slides up that some people here may not know Bunsen. Anybody take high school chemistry?
Oh, yeah.
Yeah, you got your Bunsen burner. Yeah. Right there on the lab desk. And if you take, as you did in high school, a little copper and put it into the flame of the Bunsen burner, it was green. Right? And you take a different metal and it'll be a different color. And this is how we found what those lines were really about. It goes back to electronic configurations. You've got your nucleus in an atom, and then you've got a cloud of electrons around it. If you do anything to disturb that electron configuration, it makes a big difference. What happens here is when you put the copper in the Bunsen burner, some energy from the flame interacts with the copper electrons, and the copper electrons get bumped to a higher energy level. They don't like being at a higher energy level, so they, as soon as you take it away, they drop back down. When they drop back down, they release the energy. That energy is released at a very discrete wavelength. You do this with hydrogen, you have it that way. Let's look at this. If you do this with atmospheric hydrogen, then you get a very discrete position of the lines. These are the individual electrons that are normally in the position for the hydrogen atom getting bumped out a little bit. But when they get bumped out, they can't just get bumped out a little, they have to go to the next level. So that next level is a discrete peculiarity for the hydrogen atom. And such is the same for helium, such is the same for copper, oxygen, everything. And we find that it works both in an emission sense and in a absorption sense. So now we can find that with those emission lines and absorption lines, you come through in an astronomy sense and look at the light coming from stars and the atmosphere, and we get those bands and we get those spectral lines for, and we can relate back to the common elements. Those lines can be recreated in the laboratory, and thus we can have a set of fingerprints for each element. And if you wonder how the astronomers figure out what elements there are when they look at these photographs, they can isolate the light coming from the stars, and they can see the absorption lines that are the emission lines that are there. And the emission lines tell them, okay, we found oxygen on planet X. Not so hard. Let's go to next thing that was on the little verse, something about redshift. From your redshift, we can tell your distance from us very well. Well, we know that things are moving away from us in general throughout the universe. There are some exceptions, and we'll get to those in a second. But when we find light from a star, we look at those absorption lines, or the absorption lines in this case, and the absorption lines are shifted. If they're shifted toward the red end of the spectrum, that tells us that whatever generated those lines is moving away from us. So the more the shift, the faster it's moving. And since the universe is expanding, we can translate that to a rough idea of the distance. Distance is important. This is the light version of the Doppler effect. You hear about the Doppler effect being, you hear a train coming, blowing its whistle, coming toward you. It's a higher frequency than when the train is moving away from you. With light, if the star is not moving, you have a certain wavelength and a certain set of absorption lines, or emission lines here, absorption lines here. And if the star is moving away from you, those lines get stretched out, and that causes the shift to the red end of the spectrum. That's kind of a neat thing. You have any questions on that for? Okay, good enough. When we send up some telescopes, we have the Hubble and the Webb that we're talking about all the time. It's kind of neat to see that the Hubble can take a picture of the sky using a certain set of filters, and the Webb can take a picture of the sky at a different, using a different set of filters. And by using the different filters, we can find the little subtleties in the colors of the objects that we're looking at. So here we see a combination of James Webb and the Hubble, and we find that some things are bright red, other things have a tendency to be blue right next to it, and that's kind of an unusual thing. This came out only a few weeks ago, so you haven't seen this one too much, but it gives you a graphic representation of near and far. We always think of these photographs as being almost on a screen at the same distance, and they're not. And I find that so fascinating to look through the telescope and have to keep kicking myself, saying, it's not a distance. Okay. Back to that Hubble. Why are we talking about the Hubble all of a sudden here? I know the answer. It's Deep Sky Object Day. And deep sky objects are things like the Hubble, the deep field photograph. They call it a deep field for a reason. And then there was a newer deep field, and there's a southern deep field, because we're looking at little portions of the night sky that don't have any bright objects in them. And when the Hubble looks at these areas of the sky, it picks up a smidgen of light here and a smidgen of light there. And if you stack that light up through a bunch of time-lapse photographs, you get a nice picture of the night sky that you can't see any other way. And when you find a teeny tiny space, a bit of space with 3,000 objects, that's astounding. That is truly astounding. So this was from way back in 1995, and a little bit about that area was right there above the handle of the Big Dipper, right between the handle and the bowl. They chose that spot because there was no bright stars in that area. No bright stars. And if you have, if you want a picture of the, an idea of the size of that little spot in the sky up there, it's equivalent to the distance, to seeing a dime at a distance of 75 feet. Now, it isn't that far from here to the back end of the room back here. If we put a dime back there on the wall, I've been known to do that, and nobody notices it. But then if I'm showing them my telescope, I can put my telescope on the dime back there, and all of a sudden they can see it. And they can also recognize that it's a dime and read the date. So but it's a teeny tiny amount of sky, and those 3,000 galaxies that you see up there, those 3,000 galaxies are repeated at every dime-sized spot all across the night sky in the northern hemisphere and in the southern hemisphere and every other hemisphere that you want to think of. You start multiplying those numbers out, I came up with you can't imagine tremendous number of galaxies, and of course each one of those galaxies probably doesn't have much more than a few hundred billion. When we look at the Big Dipper, which we did back in some of the other things, some of the other lectures, we find that it's a good help to use it to try to find a way to deal with all of these huge numbers of things in the sky. When we look at any of the constellations, we can use them as a roadmap to get to where we want to look at things. If we look at the handle of the Big Dipper, we can follow that around to find Arcturus. Remember, Arcturus was the first big star next to the sun that we found. So we find Arcturus by chasing that around. We also can continue that arc to Spica. So we can arc to Arcturus and spike to Spica. And all of a sudden, we look at the Big Dipper up in the sky, and we can find two more stars and recognize the constellations that they belong to. And that just kind of helps us get started on this business and on that. We also recognize that we want to talk about individual stars. So we always take the brightest star and give that the alpha and the beta and so on to try to help us make sense out of the brightnesses of stars. And we can also compare those brightnesses to the brightness of, say, a deep sky object. If we look at the brightness of a deep sky object in comparison to a known brightness star, oh, okay, that has a magnitude of such and such. Put numbers on things, and it helps us to deal with them. Now, also to deal with these objects, some of you looked at the table back there, and you probably saw that I brought in a copy of Burnham's Celestial Handbook. Well, that's the third volume. There are two others just like it with different parts of the sky. So we've got a stack of Burnhams about that high, and each one of those pages has a ton of information on deep sky objects. It's not the only catalog. There have been a lot of different catalogs, and of course, one of the earliest ones was with William Herschel. And I didn't note any more than that was back in the 18th century. So in the 1700s, they simply cataloged the locations of things in the sky, and that led up to the to the new general catalog, which contains thousands, maybe 10, 15,000, I don't know how many. And we refer to some of the deep sky objects by their NGC number. So you'll see that as a way to talk about this object or that object. We're going to get to the pictures in a second. But first, we'll stop at the next catalog guy. Charles Messier did it for a different reason. He was a comet hunter, and as you can tell, he was looking up at the sky in the same period of time as what was the name of that guy that had the comet? Halley. He wanted to be famous like Halley. And in order to be famous like Halley, you had to find comets. If you found things in the sky that didn't move from night to night to night, just were the same faint fuzzy, staying where you saw it the first, well, you went back to it night after night after night, and when you were going back to it night after night after night, you were wasting time. I want to talk about the important stuff, get comets. We don't care about that faint fuzzy stuff. Now, we like those faint fuzzy things today because the Messier catalog of 100 items at the time, and there have been 10 items added to it. So we have 110 items in the Messier catalog now. And the reason astronomers like those is that those are some of the most interesting and beautiful of the deep sky objects. So let's then go over here and look at something that precedes looking at the deep sky objects. Very briefly, what happens is that when Jerry goes out on the deck or to the star party, he doesn't go immediately to deep sky objects. I want to check the optics on my scope. I want to make sure that I haven't nudged my focus or something like that. And the way to do that is to look at alberio. That's my excuse for doing it. Alberio is what I go to when I start viewing and when I finish viewing, because it's beautiful. It just knocks my socks off. I love this thing. We've got this beautiful orange and blue combination, and I can look at it for a long time. But I'll look at it for a few minutes and say, okay, optics are pretty good. I'll go elsewhere up here. Alberio is down here at the head of the swan. You sure that's the head? Yeah. Denham is at the butt, and then the swan's wings are out here. Also here, this referred to as the Northern Cross, and you can find it on your sky charts, of course. It's pretty easy to find. You want me to do that now, or you want me to go on?
Move on.
Oh, can't go on yet, because the next slide shows M27. M27 would be, of course, the 27th item that Messier found and put in his catalog. You'll see that in the next slide. Before we leave, M57 is over there. We're going to see that too. So we use the constellations to help us find things. Doesn't get any better than that. Gives me a chance to look at alberio. I know that if I just go to alberio and take a quick right, I can get over to M27. And if I take a quick left, I can get to M56. And then if I want to, I can also just look at Vega and get a little bit of the harp going for me there and find M57 pretty easily. But let's look at M27. We also see that when we find the opportunity to go look for M27, it has a new general catalog number of 6853. you could use either one. You can use them both. 1764, we had the Dumbbell Nebula, and this was done by J. Williams, one of our Stargazers. And Jay has a nice telescope. He took this for 76 seconds to gather enough light to give us that nice, I like to think of it as an hourglass. What? What is it? What?
Jay Williams. Is he here?
No, I didn't.
That's what she said.
That is the Dumbbell Nebula. And we're going to look at this a little bit more, or talk about it a little bit more as a planetary nebula, because that's a very important category of deep sky objects. We switch over to another deep sky object, M11. This is known as the Wild Duck Cluster. It's in Scutum, but very close to Sagittarius. And they thought that it looked like a bunch of flying ducks. And Jay Williams shot those ducks. And we're, of course, talking about it here because clusters are very important. This is an open cluster. It is a bunch of gravitationally attracted stars in a very tight position within the spiral arms of the galaxy. So inside the spiral arms of the galaxy, we find open clusters. These are simply bunches of stars that have been gravitationally pulled together, and they're just, think of them as a bunch of roommates having a party. Just people come in from all over the place, and in the case of these stars, the stars are kind of coming in from all over the place and giving you these open clusters. Some of them are nicely bunched like this. Some of them are mostly space. Now, Jay also took a picture of the Trifid Nebula. And the Trifid Nebula, a lot of information up there. We have a blue reflection nebula, a red emission nebula, and we also have lanes of dark nebulosity. The nebulosity is essentially dust messing up the picture. The blue is hard to tell. There's a blue here and the red here. And that's a Sagittarius also, and the name means three-lobed. And if you see Jay, tell him I put his slide up there on the thing. He had to keep his telescope on this for 100 seconds to get even that faint unenhanced photograph.
Here,
Going to,
here,
yes,
did you ever explain locations in space?
I could.
You haven't done it. You're not
You're
playing.
talking about the Trifid?
Or I don't know what, I just thought
Okay.
Jay Williams had a location in space on that slide.
Yeah, when Jay
Wonder
is
how he got that.
when Jay is taking his telescope and pointing it at one of these things, he tracks the thing, so it makes up for the movement of the Earth. But this is Sagittarius area here, and this is where those items are located. So the ones that were just showed the slides of, the Wild Duck Cluster is up here, and the Trifid Nebula is right here. And I didn't show you one that is called the Lagoon Nebula right here. Once you get started in Sagittarius, it's hard to stop. And we don't have enough time to go through all of Sagittarius even, because there's just too darn much there. There is one that you can probably, I don't know if it's this spot right here, but we have a number of globular clusters, which are probably the leftover nucleus of satellite galaxies that the Milky Way has stripped off the other stars from. So when you have small galaxies and they start orbiting or interacting with the Milky Way, the stars that are further away from the nucleus just simply get assimilated into the Milky Way, and you're left with the nucleus. And sometimes those nuclei have their own little black holes and things of that type. So you have that. Yeah, there's just too many things to do. We have M21 here, M28 here, M this, M that, M this. They're all over the place in Sagittarius. And this is why the star chart becomes a very important thing. As I was saying before, if you're going out and you're trying to find these things, you need a map. And the sky map is a good place to start. The things that we're not seeing right here so far are those galaxies. Let me see what we. Yeah. Let's stay with the other things here first. In Orion, and you'll see Orion, I believe, in the lower west on your star chart, your sky map for this month, and you see Orion down there. It's one of those constellations that really looks like it is something. It's the Hunter, and it looks like a Hunter. And besides that, we've got this nice belt, and that makes it very, very easy to find. We also see Betelgeuse and Rigel, and as I said before, while Betelgeuse is considerably larger, it's a red giant, then Rigel is actually brighter than Betelgeuse. They look about the same there, but technically Rigel is a little bit brighter. And we want to look at two other items here while we're doing this. We've got the Horsehead Nebula, and we also have M42. And the reason I picked those in Orion is easy to find, and so are the locations of those two objects. These are examples of easy to find and look at, and difficult to find and look at. This is the Horsehead. And this is what Jay did with an 11-minute exposure. You can see the Horsehead right here a little bit. That's what it looks like if you have a Hubble with enhanced optics and computer graphics. So you can really bring out that Horsehead if you've got the right equipment to do so. And it's a very famous nebula because it's cute. But you take that out and point it up there at the Horsehead in Orion, and you're going to see some nice dark sky. No little horseheads to bother you. M42, on the other hand, is in the sword of Orion. We go back right down here. We have the belt of Orion here, and the sword is hanging down from the belt. And M42 looks like that third star in the sword. But even through binoculars, it's spectacular. And what we find here is essentially an emission nebula, and it's illuminated. This is all illuminated by new bright stars here in the center, in the core of M42. Now, it's an easy object. We can take that telescope, which I'll show you in a few minutes, and we can point it at that little cluster there, and we'll see 4 stars just nice and tight, the trapezium. It's a good test for optics in a smaller scope. I have good optics. Let's see how some of these things were made. In the beginning, we had gases. Those gases had gravity. So the gases condense over millions and millions of years into protostars. The protostars, depending on the amount of gas, either formed a big star or a little star. Our sun is in this sequence over here. And what we get are the sun as it is right now. It will become a red giant. It won't go nova, but it will become a planetary nebula and white dwarf. If it's larger, then we go from a large star to a super giant star, and it will end its life blowing up as a supernova and give you a black hole and a neutron star. That's how these things come about. Okay. The way it works is that you have originally hydrogen in the gas. When that hydrogen gets condensed and the pressures build up, especially in the core, the heat builds up in the core, you get very, very high temperatures and no wiggle room for the hydrogen atoms. They get squeezed together, and they get squeezed so tightly, they'll form helium. When that happens, the amount of energy in the individual hydrogens make up a greater energy than you find in the helium that they make. And energy is kicked out. That energy starts out in the form of those very, very high energy gamma rays and works its way out of the star into space. Some of it gets headed right toward us and we can see the star. Now, when the hydrogen in the core runs out, you get an initial contraction, and then the outer shell of the star, which is still all hydrogen, it starts to expand and you get into a red giant. So that's what's going to happen with our star. It's red, it's going to be red because it's cooler than it was in the main sequence, and it's a giant because the outer shell has expanded outward. And that outer shell will actually get out as far as the orbit of the Earth with our sun. So start out, run out of hydrogen, go to the red giant. When it gets to the red giant stage, helium fuses into carbon, and then the low mass stars like our sun, after the helium is fused into the carbon, then you get a collapse, and as the core collapses, the outer layers of the star are expelled, and you get a planetary nebula. And the core stops fusion, can't go any further, and eventually it starts out as a white dwarf and becomes a dark cinder in space after much too long. I won't be alive. Okay. Now, that planetary nebula looks like that. Say, well, that's not much. Well, that's what I get with my telescope. And I think it's kind of cute. I get this cute little donut. And it looks like that. Now, keeping my fingers crossed because Christmas is coming. And if I get a Hubble type telescope, then I can do that. I can get M57 the ring. I told you when we were looking at Cygnus back then, if you go one way, you get M27. You go the other way up in Lyra, you get M57, little donut up there in Lyra, and that's it. And of course, with that Hubble, you can see the white dwarf in the center. You say, okay. Now somebody already ahead of the game here, they say, but Jerry, you said all the fusion stopped when you got to carbon. How come we can still see it? I know, that's what you're thinking. Have you ever seen a coal-fired forge where the blacksmith puts the iron rod into the coals and gets it nice and hot and all that? Takes it out of the coals, but you can still see it glowing, first red, first white, and then red, and it continues to glow until it cools off enough so you don't see it anymore. That white dwarf is going to cool off after a while, and that's what you'll get. Now, in the case of supernovas that happen after you get big stars, gravity pulls them all together, you get the same carbon business, fusion, and get up to iron. It'll go a little bit further because the star is a little bit bigger, and you can eventually find the iron being generated, and when that happens, it stops. Because iron, just coincidentally, is the most stable of all the elements. Right there in the middle of the periodic chart, but the configuration is very stable. It's just got that sweet spot of protons and neutrons and electrons. And it takes a lot of energy to do anything with it. And from an element making business that goes on in stars, up until iron, the fusion process was kicking out those gamma rays. When you get to iron, it starts needing energy. And what happens when it starts to need energy? Bang. You can't fight the gravity if you're not pushing out energy. And the gravity is so great in these massive stars that it bangs together and crushes everything in less than a second. It hits over 100 billion degrees. Now you say, well, you know, that's hotter than I'm accustomed to. Yeah, well, it's unimaginably hot, but we can calculate these numbers. 100 billion degrees, it's just a silly number. It's hotter than that. Okay, so we get the supernova, and the supernova, of course, blasts everything out except at, the remainder core. So we blast out all these elements into space, and they become part of new stars like our sun. And if it's only 1.4 times as massive as our sun, that's the leftover core, not what we started with, but the leftover core is still bigger than our sun. If it's that big, it continues to collapse, and you get a neutron star. When I was growing up and starting to learn about astronomy in the 50s, they were talking about these neutron stars, and they were calculating things, and I thought that it was actually something that we had seen, something that actually was possible to look at. No, not so. As a matter of fact, the neutron star, we're going to see in the next slide, is a tough object. Well, how were they talking about that in the 50s? Well, because that doggone Einstein came up with these formulas and were able to calculate what was left over. And they were telling me in the mid-50s that a teaspoonful of neutron star would weigh 5 to 10 tons. We've upgraded those numbers. Now it's maybe a few hundred tons per teaspoon. There's no room for atoms to wiggle in the neutron star core. Atoms can't exist there. The temperature is too hot. The pressure is too great. It's just a big bunch of quantum plasma. No elements. Nothing. And that's a neutron star. And of course, after that, if it's more massive, then it collapses more. The nature of the remnant that becomes a black hole is going to be of the same type. It's going to be so dense that not only does light not escape, but it can't exist as atoms. It continues, and that's why I put down here that the core continues to collapse, because you'll hear your TV astronomers sometimes talk about, well, this is what, no, you don't know, and you never will, because you can't get close enough to it and you're not going to see it. You could probably do a better calculation in maybe 200 years or 1,000 years, but you're never going to see it. Don't talk about it. And you're never going to visit it. You stay away from all black holes, neutron stars, sun-type stars, and everything else that's big and bad, because it'll hurt you. It won't just hurt you. It'll hurt you before you get there. So we don't even worry about that stuff. But with a black hole, even light can't get out of that gravity trap. And that's all it is a gravity trap. Other than that, it's just a big bad mass of plasma. Now, that was up until 1996. In 1996, well, we had been charting neutron stars as X-ray emitting objects. So those high energy crushed neutron stars were emitting X-rays, and they still are. We have hundreds of X-ray items, X-ray objects that have no apparent visual component, but they nailed down the location closely enough in 1996 of one of the pulsars, and that pulsar was up here, and they trained the Hubble there because of the location of that X-ray signal. So this is the first picture in 1996 of a neutron star. That neutron star, remember, is much larger than our sun is right now. That was the size of the original core that was left over after the supernova, and it got squished down to about 17 miles across. That's a lot of stuff in almost no space at all. And of course, it's still just a cinder up there. There can be no fusion because there are no atoms. It's just quantum particles and gravity. That's all it is. But it's still hot. And like that blacksmith's forge, that neutron star is still visible until it cools off. Now, how many are out there that have cooled off? And, I don't know. Can't see them. No more X-rays either. So that's the neutron star. And then we've got one more little thing to talk about. And this is the last of those objects that, even though it isn't big enough to start the fusion process, a brown dwarf is nothing to mess around with. Because it's a lot of stuff, a lot of gravity. Don't go there. Stay away from that. It'll hurt you. Okay? That's a brown dwarf. And we find that we have some brown dwarfs close by. And they're just not enough to get cranked up yet. But when gravity squeezes things, even though the fusion hasn't started, the squish is producing enough heat so that we get infrared. And the infrared radiation, if we look, let's think back to that spectrum, infrared was just to the low energy side of the visible spectrum. And low temperatures on the brown dwarfs, low energy radiation, and that's bingo. Now, the lumen system is the closest one to us, not very far away. The nearest star is 4.3 light years away in Alpha Centauri system. This is 6.5 light years away, not very far away, and that's what it looks like. Gee, how'd they get a picture if it isn't making fusion? Well, because we have X-ray or infrared sensors on our telescopes. So we get the infrared spectrum and we can identify the source. A little better detail here, and bingo. We have a binary brown dwarf, and it's pretty close. Too far to go. We'll never go there. But this is from the Wide Field Infrared Survey of the Explorer satellite. And then you get the Gemini multi-object spectrograph giving you the inset up there. So these are infrared pictures, and kind of nice. They're just up there glowing because of the heat of the gravitational compression. Okay. And that's all we have. So, do we have any other questions? Any questions at all? Okay, let's play with the telescopes. Okay. Leave that up there. Yes.
You may want to mention the astronomy calendars that you get for Christmas, rightfully from your children.
Yes.
We have a couple of examples back there. If you look at the back page, you will see some of the pictures that are in the calendar, and some of them you mentioned. You mentioned the horse head. You mentioned various ones with the numbers, the NGC catalog, and the Crab Nebula, and you can take a look at them, and they're very pretty. We only have 3 calendars because somebody made me throw out the old one.
Oh, what person would do that?
I throw them out.
When you put that back there, would you turn on one of those lights in the front? Thank you.
All right.
Hey, some of you have been wondering about this. Gee, it's not even set up yet. Why is that?